Who's got questions? No one? Okay, then let's take a look at today's lab. Oh, let's take a look at today's lab. So I'm going to change a share here. And I'm going to share my browser. And this is our lab, this acid-base reactions. So I'm going to go through with you how to collect the data, so to speak. Not so much the background. I'm going to let you read the background yourself because there's quite a bit there. If you look at the submit has images of your lab write-up from the lab notebook, images of the results of the sulfuric acid, hydrochloric acid, sodium hydroxide solutions added to the cups. Make sure the cups are labeled, blah, 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 blah. Image of the redox reaction with the penny and the vinegar. Image of the gas forming reaction, and answers to the assignment. So in the background, I talk about acid-base reactions. And in these acid-base reactions, I talk about how you balance them. I talk a little bit about different acids and different bases. The net ionic reaction. Redox reactions, I tell you how to figure out that you have a redox reaction and how to analyze them. And in the gas forming reactions, there's 4 of them in the book. And so you want to take a look at those. They're in a nice little table, easy to read. So we're going to be doing all of these in this particular lab. You should wear goggles when working with acids and bases. And here's the materials you're going to need. You're going to need a penny, minted after 1983. I've got one of those here somewhere. I don't know what I just did with it. Oh, well, I'll have to get another one. Okay, you'll also need vinegar. Actually, you don't need vinegar. You're going to need a metal file or access to a concrete sidewalk. If you can't find a concrete sidewalk, a rock will do. Red cabbage, baking soda, 4 clear and colorless cups or with a white interior. So these are my cups right here. Nice white interior. I already said red cabbage. The 0.1 H2SO4, the 0.1 HCl, and the 0.1 NaOH. That comes in your little packet for the acid-base reactions. Okay, so for the redox reaction, you're going to need a penny minted after 83. So here I have a whole bunch of pennies, and I'm going to change my share in just a moment so you can see what I'm doing to the penny. Oh. And don't hesitate to speak up if you have a question. Okay. So hopefully you can all see my penny here. I'm going to zoom in on it a little bit. And from the date, you can see it's 2000 something. So it's clearly after 1983. Oh, I just found my penny. So here's my other penny. So here I have a nail file with some clippers. And I just want you to take the penny and I want you to rub the edge of the penny. So here I've rubbed the edge of the penny, and let's take a look at the edge of the penny. Can you see how I've roughed up the edge of the penny? And the roughed up edge of the penny is not copper colored anymore, it's silver. And it's silver because what's inside the penny is zinc. It's only copper coated. The reason pennies are copper coated is to protect them from reacting with the oils in your hands and so forth and so on. So that's why we like copper coated pennies. The reason we don't have copper pennies anymore is because if you did that, pennies would cost more than a penny to make. Just because the copper alone would be worth more than a penny. So they used zinc, which is inexpensive, and coat it with copper to protect the zinc from reacting. So you want to scratch the edge of your penny so that you have that silver spot, and you want to know where you scratched it because that's where the reaction is going to occur. And you want to take your penny and put it into a glass with a cup of vinegar and just leave it there. And probably it's best to use a clear cup, clear glass. And you want to take a look at that penny in the vinegar after about half an hour and then another half an hour. And you should see something happening at the edge of that penny. And it may take a few times to see it. So you look every half hour, maybe it takes you 3 hours to see something. It may take less, I don't know. I just know that when I threw a penny in the vinegar, I forgot about it and didn't look at it till 3 hours later, and I saw something happening. So you could watch a movie. I want you to take a photo of the reaction that's occurring, and that's going to be one of the things you submit. So this is a redox reaction. And I talk a little bit about that redox reaction in the lab itself. So I'm going to change my share back to this, the lab. And so here's the procedure for the redox reaction. Take the penny, put it in a cup of vinegar every half hour. Take a look at that sucker and take a picture of it when you see something happening. Any questions about that one? Okay, there being none, the acid-base neutralization reaction. What you want to do is you want to do some acid-base reactions, but to be able to see acid-base reactions happening, you need a pH indicator. And so the pH indicator you're going to make is one where you use red cabbage and you boil it in water. Or you could blend it in a blender with water. You don't need to heat it up. Let me show you what the cabbage looks like after you've boiled it in water. So I'm going to change my share. Okay, so here's my pH indicator. It's the cabbage juice after I've boiled it. And I only boiled it for about a minute. And then I added some water to cool it down. So it should look like a bluish color. Now what I'm going to do here is I'm going to get rid of this pot and I'm going to put 3 cups down. You really need 4. I only have 3. I'm going to zoom out as much as I can, and then I'm going to take some of this cabbage juice and I'm going to put it in each cup. Basically enough to cover the bottom of the cup, and that's it. Okay, so you should have your bag of stuff from the acid-base reaction. And when you open this up, you want to make sure you keep track of what's what. You have 3 pipettes and you have 3 containers of acids and bases. So I'm going to move these over. Whoops. I got my paper towels here so I can dry things off. I dumped some of the stuff out of one of these containers, so I have to add a little more to it. Okay, so I'm going to put those off to the side so that you can see the acids and the bases. So here, this is sodium hydroxide. This one, it's a base. This one is hydrochloric acid. It's an acid. And this one is sulfuric acid. It's an acid. So basically, if it says an acid on it, it's an acid. If it doesn't say acid, it's a base. And we have definitions for those in the chapter. It's actually part of your assignment to be able to define those things. Okay, so I have 3 pipettes. And to keep track of things, what I'm going to do is I'm going to write on my pipette HCl, NaOH, and H2SO4. And that way I can keep track of which bulb goes to which container, because you don't want to cross-contaminate. Okay, so here you want 4 containers, and I only have 3, so I'm going to cheat and use this as my 4th container right here. And I'm going to turn the light on this thing so that maybe we can see all 4 containers at the same time, and we can see that the colors are pretty much the same. So can we see all 4 of these? I can't. I'm going to shove these 2 over, and these, that's a little better. Okay, they all should look the same color. And the reason they don't is because the lighting. So what you're supposed to do here is, I'm going to put my goggles on. Now the concentrations of these acids and bases are very mild, but just to be safe, I'm going to wear my goggles. To give you an idea of how mild they are, the acid in your stomach is about 10 times stronger than the acid I have here for the hydrochloric acid. So 10 times stronger. So that, in other words, this is 10 times weaker. So what you want to do is start with the sodium hydroxide, because you have a lot of that and not much of the others. And if you're going to run into troubles, the trouble will be that you run out of something. So start with what you have most of. And I'm going to open this up carefully, and I'm going to grab my sodium hydroxide pipette, and I'm going to put some of the sodium hydroxide in my pipette, and I'm going to add this to one of these containers drop-wise. So 1 drop at a time. And I'm going to look for a color change. So do you see how if I have this next to this, I can see that the color is beginning to change? So one of these is a control, so we know what it used to look like. And so there's a color change. I'm going to add another drop. And it looks like it's changing a little bit more. And a little bit more. And a little bit more. A little more. And we want to add 6 drops. Okay. So now I'm going to show you how to screw this up. Because we all want to know how to make a mistake, right? And so that you can avoid it. So in this container, I have quite a bit more solution than in this container. And what I'm going to do is I'm going to add the sodium hydroxide to this container dropwise. So here's 1 drop. And can you see that the color doesn't really look like it's changed? Here's 2 drops. 3. And now I can tell it's starting to change color, but it's still tough to tell. So what am I trying to help you with here? I'm trying to help you with the idea that if you want to make a solution basic by adding sodium hydroxide to it, the more solution you have, the more drops you have to add. So if you start off with less solution like this cup here, you'll see a change more immediately with fewer drops. Does everyone understand what I've just gone through here? So don't use a whole bunch, use a little. So now I need another container, hang on. So I need a container to put my used stuff into. And I'm going to go back to having just a little bit in this cup. So right now I'm rinsing it out. Okay, so I've got a little bit in this cup now. And here's the other one. So this one here is going to be my control. And you can see that these three on kind of on the right all look pretty similar to one another color-wise, correct? So I'm going to grab my pipette that says HCl on it, and I'm going to grab my container that says HCl. And I'm going to add drop-wise HCl to one of these. So 1, 2, 3, 4, 5. I think that's 5, 6. So you can tell that there has been a slight color change when I add the HCl to the solution, right? Here it's I would call this control more of a steel blue, if you will, and this one more of a, I don't know, blue. And you want to do the same thing for the sulfuric acid to the third one. And you want to keep track of these color changes. Okay, so you're going to have to be kind of descriptive. Like this one looks more like a, now that I look at it, it looks more like it's got a reddish hue to it. And just to show you what I mean, if I kept adding the HCl, do you see where I'm adding the drops in? It turns pink. And if I swirl it, whoops, I spilled it. You can definitely see that it's turning purple, right? So with that in mind, I'm going to go ahead and take these two solutions and put them in here. And I'm going to put some more cabbage juice in those two containers. So here we go. And they're all pretty similar in color again. And I'm actually going to dilute these a little bit with water. Let's see, where's my water? I got to go grab my water. I'm going to go ahead and make my solution just a little more dilute. So I'm going to put them all in the same container. That way they all have the same concentration of indicator in there. And so that's a little more dilute. Put a little in there too. And I'm not using any sort of special water here. It's not distilled water, it's just tap water. So I'm going to pour a little bit of this into each container. And hopefully they all look the same color. Okay, so they pretty much look the same color. So that was the first part. And, you know, after you put the acids in here and after you put the bases in here, I want a photo of all 4 of these. And I want to see what final color they have become after you've added the 6 drops. So let's go back a bit. I'm going to do a different share. So what am I talking about for the photo? If you go back up here to the submit, do you see where it says images of the results of the sulfuric acid, hydrochloric acid, and sodium hydroxide solutions added to the cups? Make sure the cups are labeled. So when I say make sure the cups are labeled, you can actually line the cups up. And you can't see what I'm doing, but I'm going to share with you so you can see what I'm doing. So can you see how I've lined the cups up? And so I could write on this piece of paper a little arrow pointing to this guy saying what it is, an arrow pointing to this guy, and so forth and so on. Now, to be able to get all 4 cups in one picture, I would actually have to have my camera farther away from the cups. So the only way I can do it at home here with this camera that I'm using is to lift it, and it's kind of heavy. So with you at home, you just have to hold your phone a little farther away from the cups. You with me? So that's the picture that I want after you've added the acids and bases. So I'm going to go back to the lab, and I'm going to let you read that part again about images of the results of the sulfuric acid. So do you understand the part where I write, then take a photo from above? So pretty simple. Now, the next thing you want to do is you get the 4 cups again, and you actually only need 3. One of them is going to be a control, and 2 of them you're going to do this with. So I'm going to change my share. So this one on the end doesn't have very much in it, so I'm going to put a little bit more. So what you're going to do with these is 2 of them you're going to add sodium hydroxide to, 6 drops. So I'm not going to bother looking at the color change as it happens. I'm just going to add 6 drops. 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. Now, water itself is a neutral solution. And when I add base to these 2, they become basic. Now, I can take a basic solution and make it neutral again. All I have to do is add acid. Now, I want to get the right tube. So this is HCl, and here's my HCl solution. Now, I'm going to ask you to add this acid drop-wise, 1 drop at a time. I'm going to do it on the end one, and stir it. And you basically want to add it until it turns the same color as the control. And you can see that It is changing color a little bit. You want to make sure you add full drops. And can you see how the color now kind of matches the original? So that means I've neutralized the base with my acid. So I am going to ask you to drop acid in this experiment, but it's all in the name of science, okay? Now, what are you going to do with this other cup? You're going to do the same thing, only with sulfuric acid, and you're going to count the drops. When you're done with all of that, it all goes into one container, and you pour it down your sink. I do not recommend drinking boiled cabbage juice. I don't think it is tasty because of the sulfur compounds in there. And now I can take my goggles off. So
I got a quick question. How much cabbage are we gonna have to boil?
3 by 3 inch, 3 inch by 3 inch piece in a little bit of water.
Oh, you're just talking just a leaf.
Oh yeah, not even a whole leaf. My goodness, no.
Oh, good, because I don't know what to do with red cabbage afterwards.
Coleslaw, man, coleslaw. Or you could make a red sauerkraut, or you could make you could use it in stir fry, or you could keep it in your refrigerator and show it to friends and say, look what I got, red cabbage, and I don't know what the heck to do with it, because I have red cabbage in my fridge and I've had it there for a year, and the only thing I use it for is this. So there are some stores, I think, where you can actually buy like lettuce that has red cabbage in it. And maybe that way you could at least use the lettuce part. All right, Greg?
Thank you.
You bet. Anyone here just love cabbage? None of us? I'm not sure what you use cabbage for. Okay. So I'm going to do a new share. And so you understand that you don't need to take a photo when you've neutralized those solutions. I don't need that. You'll notice I have an image of the redox reaction with the penny and vinegar. Okay, so we've actually done quite a bit. And the last little bit here that I want you to do for me, you want to do in a sink or outside. You want to do a gas forming reaction. So here I have, place a cup of vinegar in a large bowl or cup. When I say large bowl, I mean a large bowl or a large cup. I mean huge, like a pot that you would boil spaghetti in. Spaghetti noodles. You with me? If you do put it in a smaller cup or smaller bowl, put that inside the large pot, because this thing's going to boil over. And you want to catch all the liquid. Otherwise, it's going to be messy. You with me? So you put a cup of vinegar into something. Actually, you know that in your box of stuff, you have what's called an Erlenmeyer flask. Let me show it to you. So this is like Christmas. Let me do my new share. So this is the Erlenmeyer flask. And when I open it up, you can see that it's, we call it conical, conically shaped. You could use this for that experiment. And if you use this, you want to put this inside of a large pot. And what you can do with this is you can do one of two ways. You can put the vinegar in first and then add the tablespoon or teaspoon of baking soda. Or you can put the baking soda in first and add the vinegar on top. Probably be work the best if you put the baking soda in first and then pour the vinegar in, because it's really easy to pour vinegar into this. To make it a little more interesting, you could add things to this. For instance, you could add red food coloring. You could add a little bit of like a drop or two of detergent. And this is a gas forming reaction, which means it will bubble. And if you add detergent to this, when it bubbles, the bubbles last longer because of the detergent. It's like blowing bubbles with those little things you buy as a kid. So you want to take a look at what happens when you add the vinegar and the baking soda together. And like I said, if you want to make it a little more interesting, you can add stuff to it. I had thought today, it'd be pretty interesting to add a cornstarch to this because cornstarch is a little bit of a thickener, right? And so it might make things a little thicker, make it look more like lava, especially if you add a little red food coloring to it. So you want to play with that. And I'm going to go back to the lab itself. And basically a cup of vinegar and a teaspoon of baking soda, and record your observations. For this one, if I go back up to the submit, you'll notice it says an image of the gas forming reaction just after the sodium bicarbonate is added to the vinegar, or vice versa. And the last part of the submit are answers to the assignment. So are there any questions so far?
Yes.
Go ahead.
Just to clarify again, are once we do the few droppers into the cabbage water, correct?
Can you repeat that? Because for me, you cut out a little bit.
For the acid base, the pictures, we take the pictures once we add a few drops of the acid into the cabbage water, correct? Like what you did in the beginning?
Right. I'm going to go to the procedure here and just let me change my share so that you're looking at what I'm looking at. And this will help you out, okay? So this is the acid-base neutralization reaction. The first step is to make the cabbage solution, right? The next step is to make 4 containers with the cabbage juice, very thin amount, right?
Mm-hmm.
Okay, so step 2 here is then add the sulfuric acid. Step 3 is add the sodium hydroxide, and step 4 is add the hydrochloric acid, each to a different cup, right?
Mm-hmm.
So 1 cup you have nothing, 1 cup you have 6 drops of sulfuric, 1 cup you have 6 drops of sodium hydroxide, and the 4th cup you have 6 drops of hydrochloric acid.
Mm-hmm.
After you've added all the drops, that's when I want the photo.
Okay.
Okay. Does that help clarify?
Yes, thank you.
Okay. Okay, so let's take a look at the assignment here, folks. According to the book, what are the definitions of acids and bases? The Arrhenius definition and the Bronsted definition. So what's really nice about books is they have an index. So let's take a look here at this index. And we're going to go for Bronsted-Lowry, since I'm closest to that. Okay, so let me zoom in on that just a little bit. Does everyone see the Bronsted-Lowry stuff in here? Now you'll notice for the Bronsted-Lowry, they have it in a couple of places. Here, this is page 709 and 709. And here, this says page 141. Where are we going to go for our info? What do you think?
141.
Yeah, because if you take a look at page 709, It's chapter 15 or 16. So we want to go to that page 141 stuff. So if we go to page 141, I'm going to zoom out. You're going to find everything you need to be able to answer these questions. So can you see this section down here, which is titled Acids and Bases, the Arrhenius definition? So that's where we're going to go for that. But in one of the questions, I also asked for acid base, the Bronsted-Lowry definition. And I abbreviate it and say the Bronsted definition. And if you take a look at the beginning of this section, the Bronsted-Lowry definition. And furthermore, this even shows you how these guys react with water. These are acids reacting with water. And on the next page, you have bases reacting with water. And here, they show you how you write out an equation to show how an Arrhenius acid is acting in water. Okay, so they show you that also. So I'm going to put that off to the side. So a lot of this lab is trying to direct you to the reading that I'd like you to do. So do you see with number one, what are the definitions? Then write equations for HCl and NaOH behaving as an Arrhenius acid and base respectively. And that's shown what it's shown how to do that in the book. The same with number three, how they act as a Bronsted acid and base with water respectively, shown in the book. And then I want you to write a balanced neutralization reaction for hydrochloric acid with NaOH and one for sulfuric acid with NaOH. This one refers to that one problem where we added base to 2 cups and then we added acid to make them neutral. So this is going to help you with that problem. And then number 5 is based on that experiment where technically it should take us fewer drops of 0.1 molar H2SO4 than 0.1 molar, M is molar, HCl to neutralize the 6 drops of 0.1 molar NaOH. That shouldn't be a comma, that should be a period. So I'm asking you why it should take fewer drops, and you should explain that to me. And number 4 should help you with that answer. Number 6, it's a redox reaction. We'll probably be looking at redox reactions on Monday in lecture, not tomorrow. I don't think we'll get to that tomorrow, but we might. And it's a redox reaction, so you want to figure out what's getting oxidized and what's getting reduced. Redox stands for reduction, that's the read, and then ox is oxidation. And lastly, for the gas forming reaction of vinegar with baking soda, you want to write a balanced reaction. So that refers to all the experiments we did. 8, you have these 4 reactions, and I tell you, one is a precipitation reaction. So that was from the last lab we did. One of them is a acid-base reaction, one's a gas forming reaction, and one is a redox reaction. So you're supposed to complete these reactions, come up with the products, and balance them. And then in number 9, you're supposed to tell me how you figured out which one was which. Because on the exam, I usually put reactions down there and I say, okay, what kind of reaction is this? Tell me why you think that's the case. So this is really good practice for the test. So any questions about your lab? All right. Well, since there aren't any questions about your lab, let's talk a little bit about some of these ideas. All right. So I'm going to do a new share. And you're going to learn a little bit about acid-base reactions and precipitation reactions, or not precipitation, redox reactions. So let me do a new share here. Okay. So I'm going to start off with acid-base reactions. So acids, basically they produce H plus in water, or they donate H plus. Now notice for this donate H plus, I don't say anything about water. I just say they donate H plus. Bases, they produce OH minus in water, or accept H plus. All right, let's take a look at some common acids. This is a common acid. It's called nitric acid. This is a common acid. It's called sulfuric acid. It's one of the ones you use in this lab. This one is called hydrochloric acid. So these are some common acids. And these acids are what we call strong acids. This is the one that you have in your stomach, the hydrochloric. Let me give you some other acids. This one is called phosphoric acid. This one's called carbonic acid. And this one's called acetic acid. These are all examples of weak acids. And we're not going to go into too much detail about strong versus weak. We're just going to leave that as that. And here's some common bases. I'm not going to bother naming those because you should know how to name those. They are all ionic compounds with the cation first and the hydroxide ion last. So, for example, the first one will be called lithium hydroxide because it's got a lithium ion and the hydroxide ion. So these are common bases, and these are all strong. And then there's some weak bases. Actually, there's only one that you need to know. This one. It looks a lot like the ammonium ion that we learned before, but it's not an ion. It's called ammonia. So you want to make sure you know all of these, and even more than this, to be honest. But this is a good start. Usually at work, when I do these demonstrations, I have someone clean up after me. And now I have to clean up after myself. I hate it. All right. Now I want to talk about something else. I want to talk about proticity. Now, proticity is basically the number of H pluses that a substance can give. So let's take a look at proticity. This is mono, and I think it's fairly obvious why. There's only one hydrogen. Fair enough? Same for this one. Only one. This one is weird. How many hydrogens do we see? Well, I see 4, but yet this is only monoprotic. So the word we write here is protic. I just didn't write it for these others. So if this is monoprotic, it means one of these hydrogens is not like the other. So you remember your Sesame Street days, right? One of these hydrogens is not like the other. Which one do you think it is? One of these 3 or that one? And it's that one. Okay? So these are all monoprotic. And then there are some that are diprotic. Can you see why this one's diprotic? And then there's one that is triprotic. Now, if you look at the proticity, you might think, oh my goodness, if this guy can give up 3 H pluses, it must be really strong and wicked. And if we take a look at the list of weak acids and strong acids I gave you, this one's actually weak. If we look at the monos, 2 of them are strong and 1 is weak. So what does proticity tell you about the strength of an acid? And the answer is nothing. Proticity is how many it can provide, but it is not about strength. There's also basicity. So lithium hydroxide would be monobasic because it has only one OH. NH3 is monobasic. FeOH2 is dibasic because it has 2 hydroxides, and aluminum hydroxide would be tribasic. So you should understand these terms: monoprotic, diprotic, etc., and monobasic, dibasic, tribasic. You should know those terms. So the next thing I'm going to do is I'm going to show you an acid-base reaction and what happens in the acid-base reaction. So this is an acid-base neutralization reaction. And you need to memorize this, that in these reactions, an acid and a base make water, and a salt. And when I say salt, I don't mean table salt. It could be table salt. But in this world, salt means the other product from an acid-base reaction that's not water. These salts are usually ionic compounds. So salt is clearly a shorter way to say ionic compound. But salt in this case refers to specifically the other product other than water of an acid-base reaction. So this is an acid-base reaction. That's an acid. That's a base. That's water. And that's sodium chloride. And this is monoprotic. And this is monobasic. So if this is monoprotic, it means that it really only has one H plus. And if this is monobasic, it really only has one OH minus. And guess what these two things combine to make? Can you guess? H2O. Two hydrogens, one oxygen. Two hydrogens, one oxygen. And a +1 sign and a -1 sign is neutral. So this is what we often call a net ionic equation. But the most important thing here is that the ratio is 1 to 1 to 1. One proton reacts with one hydroxide to give you one water. We use that idea to help balance acid-base reactions. 1 to 1 to 1. So let's balance an acid-base reaction. So here's my acid. And here's my base. Now, can we see that this is monoprotic? And this is dibasic. So we don't have the right ratio for an acid-base reaction. We want 1 to 1 to 1, or 2 to 2 to 2, or 3 to 3 to 3. So we have two hydroxides here, and we only have one proton. It's easier to add another proton so that we have two protons. How do we get a second proton here? Now remember, for balancing reactions, are you allowed to change the formula? Are you allowed to change the coefficient? So if I put a 2 here, even though this is monoprotic, we now have two protons. Now, if I have two protons and two hydroxides, how many waters do we make? Remember, it's 1 to 1 to 1, or 2 to 2 to 2. So you make 2 waters. 2, 2, 2. Now let's take a look at what's left over. Can everyone see that there's an iron ion left over? And there's 2 nitrates left over. There's your balanced reaction. So after I used the 2 hydroxides and the 2 protons, all I did was take the rest of them and put them together. And when I put them together, of course, I put the cation first and the anion second. So your turn. balance that reaction, and come up with the products. Okay, I got a question for you folks. I'm looking at the TV and apparently a rover landed on Mars. So we sent a rover up to land on Mars to do little.
That happened this morning.
Yeah. So they showed that to help slow the descent, there was a parachute on the rover. The fact that there was a parachute on it tells you what about Mars?
That it has a gravitational pull.
Nope.
Has air, has something in the air.
Yeah, it has an atmosphere.
Yeah.
You don't know what's there, but it has an atmosphere. Because I tell you what, if they sent a rover to the moon and they put a parachute on that sucker, that thing would hit the moon really hard because there's no atmosphere. And that's why you never want to open up a restaurant on the moon. It has no atmosphere. Okay. So would everyone agree there's 2 hydroxides and 1 proton? So we want to put a 2 here. So now we have 2 protons and 2 hydroxides. We're going to make 2 water. And what's left over? Well, the chromium is left over. And the 2 chlorides. And you're done. Now I'm going to give you a real hard one. Balance that reaction and come up with their products. When you're done, give me a little thumbs up or some sort of sign. Two and three. What are you going to do? You have 2 choices. 1, curl up into a fetal position and say, it's going to be okay. Or 2, let's change some coefficients and make a match. Let's go with 2. What common thing do these factor into? 6, right? I want 6 protons. Here I get them 2 at a time, so I'm going to put a 3 there. And now 3 times 2, I have 6 protons. To get 6 over here, I'm going to have to put a 2. So now I've got 6 hydroxides. How many water are we going to make?
6.
6. Now, what's left over of the cation? It looks like 2 of them, correct? 2 of them. What's left over of the anion? The sulfate. 3 of them. So how does this look for 3 sulfates? Good or bad?
Add.
Bad. That's 43 oxygens. There's your balanced acid-base reaction. Any questions about that? So when you balance these things, the first thing you have to do is recognize the acid, recognize the base, and make sure you have equal number of H pluses as OH minuses. So this is your acid. This is your base. And what do acid-base reactions do? They make water and salt. So remember how I told you salt is another word for ionic compound formed in an acid-base reaction? That is salt. That is salt. That is salt. It's not table salt. Table salt is NaCl. Okay? So when I say it makes water and is salt, I don't mean that. Okay? So I got to leave you with one stupid joke at the end of the day. That was it. For the redox reactions, I'm going to leave you to read a little bit about that in the lab and in your book. And we'll probably be covering most of that on Monday. But it does help to read about that beforehand, especially assigning oxidation numbers. And definitely watch the lectures because we talk about it in there too. All right, folks, thanks for showing up. I appreciate it. I hope you learned a little bit and have a little bit of fun with this lab, but be careful when you're working with the acids and the bases. Capiche? Okay. Mic's off. Say goodbyes.
Later, Tony.
Bye, thank you.
Y'all have a good evening.
You too.
Bye-bye.